In section 9.2, we're going to take a look at compound inequalities. So let's take a look and see how we define compound inequalities. Anytime we have two or more inequalities that are joined with one of these two connectives, it could be an and or an or, then we call that inequality a compound inequality. Just like compound statements that are made up of two or more statements that are joined with or and in regular English classes. Now, if the two statements that are joined together are joined with the connective and, the statement is called conjunction. And if those two statements are joined with the connective or, we call the statement, or the inequality in this case, in our case, would be, we call that statement a disjunction. So remember, conjunction, the connective is an and disjunctions, the connective is going to be an or. Now, when is a conjunction true? When we're talking about the logic of a conjunction, for us, a conjunction is logically true. Remember, those are the statements that are connected with the connective and. Okay, so for these types of conjunctions to be true, the solution must work in both statements that make up the conjunction. Okay, the statements on either side of the keyword and. So remember, solution must work in both parts. Now, for a disjunction to be logically true, the solution may work in one or the other, or both. So it doesn't necessarily have to work in both of them, as was the case with the conjunction. So it could work in either or it could actually work in both of them. We will do examples where I clarify how it can be in both of them. So it's important to note that the use of or in the context that we are using here, the connective or, we use it in its inclusive form, not the exclusive form of or. The difference would be this. Let's say you go to a restaurant and you order your entree. And suppose your entree, your dinner, comes with a choice of soup or salad. Now, the use of word or in that context is it's in its exclusive form. So that means you have to choose one or the other. You cannot choose both soup and salad. Whereas in our work, the way we work it would be as if the waiter or the waitress asks you, would you like soup or salad? And you're going to say, I want both of them. So that would be the inclusive form. So in everyday life, we typically think exclusive or, but again, in mathematics and statistics and most sciences, we think of it in its inclusive form. Okay, so I just want to clarify that. Now, let's take a look at an example. So we're going to begin with this example. This is exercise number 34 in your textbook. And in this exercise, we have a disjunction because the connective is or. Now, we don't have to really solve for x in this case. The expression is already solved. So all we have to do is actually graph this inequality and rewrite the solution in graphical notation and interval notation. So now if I graph this inequality, here's 0. This is a number line. My reference point 0 is here. So let's say this is 1, and here somewhere out here is -5. Okay. And remember, on both ends of the number line lie infinity and -infinity on the left side. Now, the first part of the inequality, that would be this part of it. So we're going to handle that part. So that part says x is less than -5. Now, with less than -5 means everything to the left of -5. And we do not allow -5 itself. It's not part of the solution. So we use parentheses. Less than means everything to the left of that. Okay. Now for x greater than 1, again, because there is no equality there, so we use parentheses and we're going to shade above 1. Okay, and we just did that part. Now, because this is a disjunction, the solution could be here or it could be here. It doesn't have to be in the point of intersection, so it could be in either or of those. So let's now write the interval notation for it. And once we have the graphical solution, and that's what the graphical solution is, the interval notation falls right from the graphical solution. So here's how it works out. Now imagine parentheses on the left side of the number line. These are always there. And here way out to infinity, there's a parenthesis here. Okay. So our solution is actually, for this part, we're going to write it as from negative infinity to negative 5. Okay, and or the right side begins at 1, just to the right of 1, not 1 itself. And it goes all the way to infinity. And there we have it. This is called the interval notation. Now, a lot of textbooks, including your textbook, actually use the union symbol for the or. That means or. So let's agree the union symbol, the U, actually stands for the word or. And inverted U, this is called an intersection sign or symbol. This represents the keyword and. Okay, so let's agree on that convention. All right. And there you go. We are done with this one. We are not solving again. This expression was already solved. So we didn't have to show steps on how to isolate x is what I mean. And there we go. Pretty simple, huh? Now let's take a look at another one. Let's say we want to take a look at, let me choose something with the word and. Okay. Let's take a look at number 39 here. Okay, so in exercise number 39, the expression is x is greater than negative 2, and this time we have a conjunction, x less than 4. So this time, because this is an and, the solution must work in both parts on the number line. Okay, so let's see how this is going to shape up. Remember, put infinity here, put negative infinity here for inequalities. And this is usually what we do. This is the center line, 0. Now, bigger than x greater than negative 2. Again, I'm working this part of that statement. X greater than negative 2. So for this, let's say here's negative 2. Bigger than that means everything to the right of it, right? So I'm going to go parentheses larger than negative 2. All the way to infinity. So anything in that segment of the number line satisfies the first inequality. Now let's take a look at this one. This time we're going to look at less than 4. So suppose this is where 4 is. Less than means we use parentheses, and then we're going to shade everything to the left of that, all the way to negative infinity. Now, because this is a conjunction, right? See the and here? That means we have to find the points of intersection of the two shaded regions of green and red. And the two intersection, the segment that's intersection of the two, is actually the part that is crosshatched. That means everything in here, the crosshatch. The solution is therefore from negative 2 to 4. And there you have it. See how simple that is. The graph really helps. So I highly recommend you do the graph before you can come up with the solution. Let's take a look at another one. Exercise number 52 this time. In number 52, we have negative 1, less than x minus 3, and less than 5. Now for this one, we have the 3-part inequality. Let's say we want to isolate x. Okay, so to isolate x, I'm going to add 3 to all parts of that inequality. So in the middle, we just have x because 3 and negative 3 add to 0. 3 and 5 make 8. 3 and negative 1 makes 2. And there you go. We managed to isolate x, and there is a solution. So on the number line now, Here we have again infinity, negative infinity. I do that in this chapter for all inequalities on my number line. Between 2 and 8, so let's say this is 2 and this is 8, right? Between them, so that means parentheses, parentheses, and this is the region of solution, that segment of the number line. The interval notation for the solution is parentheses 2 and comma 8, close paren. And that is the solution to exercise number 52. Let's take a look at another one, this time number 56. In exercise number 56, the inequality is negative 4 less than or equal to 3n plus 5. And so here's a conjunction again. And 2n minus 3 is less than or equal to 7. So remember, we want to isolate the variable first, then we graph it and go from there. So to isolate, I'm looking at the first one. I'm looking at this one for now. Okay, so to isolate n, we're going to subtract 5, right? Subtract 5 from both sides. And that makes it negative 9 less than or equal to 3n. And then divide both sides by 3. Because I'm dividing by a positive number, there's no need to change the inequality. Now, with our inequalities, I like to have my variable on the left side. Okay, it just makes shading a lot easier for me. So the way this inequality right now is reading, this one, it reads negative 3 is less than or equal to n, correct? Negative 3 is less than or equal n. With your inequalities, if you look at, for example, the inequality symbol, and this is like the left part, this is the right part. Okay, now if you think of this inequality symbol and extend it, turn it into an arrow. The arrow points to smaller expression. You see that? So what's on the left here is going to be smaller, and to the right is going to be larger. So in here we're saying negative 3 is smaller than n, right? Or equal to, but I'm focusing on smaller than n. Well, to say negative 3 is less than n is the same as saying n is bigger than negative 3, true? So I swapped out the variable from right to left. So this is again going to help me with the solution on the number line. It makes it a lot easier. Okay, now let's take a look at the other. So we're done with this one because we isolated it. Let's take a look at the other inequality. And this is going to be and. So we're going to isolate n. So I'm going to add 3 to both sides. That makes this 2n less than or equal to 10. Divide both sides by 2, and n is less than or equal to 5. Okay, now we have two inequalities. Both of these are solved for n. Next step, we're going to go to our number line, and here's my number line. Remember, negative infinity is here, infinity to the positive side is 0 the center. Greater than or equal negative 3, so let's call this negative 3. Greater than or equal to it, so this time we're going to use a bracket. And bigger than that means everything all the way to positive infinity on the right side. Now the other inequality, n less than or equal to 5. So let's say this is where 5 is. So here's 5. And again, because equality is in there, see the equal sign in both of these. So we use brackets. And less than or equal 5. So I'm going to actually shade like that. This is a conjunction, true? So the solution again must work in both parts of that conjunction. As a result, the solution is going to be bracket negative 3 comma 5 close bracket. And there we have it. That's the solution to number 56. Let's take a look at another one. This time I'm going to take a look at number, let's go all the way to 76. In number 76, the expression is 2x minus 1 greater than 5 and 2 negative 3x is greater than 11. Okay, and we want to solve this inequality. So I'm going to isolate x, add 1 to both sides. That makes it 2x bigger than 6. Divide by 2 and x is greater than 3. Box that. This is a conjunction. That means solution must work in both parts. Right? First inequality as well as the second one. Let's isolate x. So to isolate x, I'm going to subtract 2 from both sides. That makes it negative 3x is greater than 9. And then I'm going to divide by negative 3. When we divide by negative 3, the left is going to be x, the right is going to be negative 3. 9 by negative 3 is negative 3. Now, remember, anytime we anytime we divide or multiply by a negative, we have to change the direction of inequality. So I'm just going to reverse the direction or sense of inequality. And now we have indeed solved both inequalities. Let's go to our number line. And x greater than 3, that's going to be 3 here. Greater than 3 because equality is not included in here. There's no equal sign. It's not like that. There's no equal sign. So that means we have a parentheses, not a bracket. So that's why I have parentheses 3 and all the way to infinity. There you go. And the other one is x less than negative 3. So less than negative 3, that's going to be negative 3 parentheses, right? Everything less than means to the left of it. And then we can actually now write the solution for this one. Remember, this is a conjunction again. That means the solution must work in both parts on the number line. Now, we have two disjoint segments. So let's say you pick a number in here like negative 5. Well, negative 5 is going to work in here. But negative 5 is not going to work in this one, right? Negative 5 is not bigger than 3. So nothing in the blue zone is going to work in this first inequality, right? Nothing in here in the blue zone is going to work in this inequality. And by the same token, nothing in this segment on the right side is going to work in the second inequality. So for example, pick, 4. Pick number 4. 4 is a solution here, but look at that. Is 4 less than negative 3? No. So there is no, in other words, region of common intersection of the two. There is no crosshatch like it was up here, because this is an AND. And unfortunately, we are out of luck with this one, and we're just simply going to say this one has no solution. And the no solutions in your book, this is how they show them. They use the notation from the sets, which is like the null sign. That's what that is. It looks like Greek phi. That's what it looks like, Greek phi. Okay, but anyway, that just means there's no solution. And let's do one last one, and we're done with this section. Let's take a look at number 78. In exercise number 78, we have 5, negative 3a is less than or equal to 8. Or 2a plus 1 is greater than 7. This time we have a disjunction. So let's just solve them first, and we proceed with all the other stuff. So I'm going to subtract 5 from both sides. That makes it negative 3a less than or equal to 3. And then we're going to divide by negative 3. So that's going to be a 3 by negative 3 is negative 1. And again, very important, we got to change the direction here. Because the reason is because we divided by negative. Okay. Or meaning this is a disjunction. Now let's solve for the other inequality. I'm going to subtract 1. That makes it 2a greater than 6, and then divide by 3. I'm sorry, divided by 2. The answer is 3, greater than 3. So here you go. We have the solution here in inequality form. Now let's go to graphical notation. So we're going to graph it. Here's negative infinity, 0, and this would be infinity. Okay. Now greater than or equal negative 1. So here's negative 1 on the number line. Greater than or equal, so we're going to use bracket. Bigger than negative 1 would be like 0, 1, 2, 3, 4, 5, and so on. Remember, the numbers increase from left to right on the number line. So bigger than negative 1 means everything to the right of that. Now let's take a look at the second one is a greater than 3. So suppose now this is where 3 is, and then I have parentheses at 3 because there is no equal sign in this one. There is no equal sign. Okay. And the solution to second inequality is actually in here. Okay, now this is a little tricky here. We have a disjunction. So that means the solution must work in the red zone or in the green zone or both. Well, this part is in both, right? This part is only in the first inequality. But for the disjunction, it doesn't care. It doesn't matter. As long as you have a shaded segment, that's all you need for disjunctions. You just need a shaded region or two. So I have check mark on both of these. So the solution is actually going to be everything from negative 1, right? Everything from negative 1 to infinity. Although 3 isn't included here, but the first inequality is okay with 3. It says it has no problem with it. So that kind of overrides this one. So all said and done, therefore, the solution to this inequality is going to be negative 1 comma infinity. And there we have that one. Okay, and there is exercise number 78 for you. So that's pretty much it in this section. That's all we wanted to talk about. So hopefully now you're comfortable with the idea of compound inequalities. And we are done with this video.